Hi, so for today we're going to talk about series circuits, and this is an introduction of how are we going to calculate such parameters: the current, the voltage, the total resistance, and power. Okay, in a series circuit, in a series pure series circuit. Okay, let me just start with. By the way, what is a series circuit? A series circuit is actually a type of connection in which the current has only one path. For every path of the current, okay, there is only one path for the current to flow from the positive side of the voltage of the battery and to the negative side of the battery. So we say that if we have a series circuit, the current has only one path. Okay, only one path. So in this video, we're going to talk about calculating the voltage drop, current, and power in each resistors connected in series. So, and we have to calculate for the total current using Ohm's law, of course, and the power in a pure series resistor circuits. Now, in a series connection type of a circuit, we have to um, somehow familiarize ourselves with the relationship of the current, the voltage, how to get the total resistance of a series circuit. Well, we know that we simply add them if they are connected in series, and the power, okay, of the circuit, total power of the circuit. So for the current, okay, if we have a series circuit, the current through each resistor, that's right, the current in R1, resistor 1, current through R2 and the current through R3 are all equal since they are connected in series. So okay, so they have the same current, and that is equivalent to the total current, okay, of the circuit. So total current is computed by the formula by Ohm's law. By Ohm's law, we have I is equals to V over R. So since this is total, we have to get the total voltage or the V sub S or the supply voltage over the total resistance. So that's the relationship the current in a series circuit. They have the same current through each resistor. Okay, in terms of voltage, okay, since these are all connected in series, we know that there is a voltage drop in each resistors. And the voltage drop in each resistor depends actually, okay, on the value of its resistance. The greater the resistance of the resistor, the greater the voltage drop according to this formula for Ohm's law. So if we are going to manipulate again Ohm's law, getting V here, so we have V is equals to IR. In a series circuit, the current is fixed, but the value of resistor actually is, for example, this R1 and R2 and R3 here does not have the same resistance. So the value or the resistor that has the highest resistance, okay, if we increase the resistance of a resistor, then definitely the voltage drop also on that particular resistor is greater than the other resistor if the resistance is greater than the other resistors. So each resistor in a series circuits has a voltage drop. Okay, and its voltage drop is given by VR sub 1, which means, or simply V1 for some other books. But for now, as we study the basics, so that you can understand the meaning of VR1, VR2, VR3, okay, sometimes it's V1 here, V2 here, V3 here. We need to actually uh, denote subscript R1, R2 to denote that that is the voltage drop at a particular resistor. Okay, if we have a series resistor, we have different voltage drops, except that their resistance is equal. If the resistance of two resistors are equal and they are connected in series, then we can say that they have the same voltage drop. But if they don't have the same, what will happen? The relationship of the total voltage inside of the circuit should be equivalent to the supply voltage. Okay? The maximum voltage, okay, in a circuit is the supply voltage. And the supply voltage is simply equal to the summation of the voltage drop in each resistor, across each resistor. So, if we have an N resistor connected in series, then definitely we have VR1 plus VR2 plus VRT plus so on and so on up to N resistor. So in this case, we only have 3, so we have to use this formula. But if it's more than 3, we have plus VR4, VR5, etc., etc., as long as they are connected in series. So again, the summation of the voltage drop, okay, in a series resistor, in a series across the series resistor, is simply equal to the total voltage source, which is V sub S or the V sub T. Okay, so in terms of getting the total resistance of resistors connected in series, it's very easy. Okay, because we simply add the resistances of R1, R2, and RT, and Viola, we get the total resistance. Okay, so it's very simple. Okay, since they are connected in series. Now, in terms of power dissipation, okay, we are going to add all the power dissipated in R1, R2, R3 to get the total power of the circuit. And if we may recall, power has three formulas. It can be current times voltage, or it can be current squared times resistance, or it can be the V squared, voltage squared over the resistance. So either of the formulas we can use as long as there's available data for current, resistance, or voltage. We can calculate the power dissipated by each resistor, and of course the total power of the circuit, okay, by using this also, using that formula also. Okay, so now that we know the basic, again, the current in a series circuits are the same. Okay, current through each resistors are the same if they are connected in series. The voltage drop are not the same except for that the resistances are equal. If they don't have equal resistance, then definitely they don't have the same voltage drop. And the summation of the voltage drop across each resistor is equal to the total voltage or the supply voltage. Okay? And to get the total resistance in a series connected resistors, we simply add the value of the resistances. And for to get also the total power, we simply add the power dissipation in R1, in R2, and R3, and we get the total power. Or we can also use the P total is equals to I total, V total. Okay? As long as all of this current and voltage are total, we are also going to find P total. Or of course, we have I squared total, okay, and then total resistance, or the Vs squared, or the supply voltage or the total voltage squared over the total resistance. So we can find the power of that. So now that we know the basics, okay, we can now solve. Okay, let's try to solve some basic problems. So for example, we have this. Okay, for number one, let's try to find the total current, power, and resistance of the given series circuit. Total. Calculate also the voltage drop in each resistor, the current through each resistor, and the power dissipated by each resistor. So we have a series circuit. As you can see, the current is actually, okay, in the clockwise direction to denote that that is conventional current flow, that is from the positive to negative. Okay, so the problem is actually asking, what is the total current? Okay, so the very first thing we find is the total current, the total power, and the total resistance. So in order for us to find the total current, okay, I sub t, we by Ohm's law, I is equals to V over R, and we're going to use Ohm's law here. So since this is total current, so this must be the supply voltage or the total supply voltage over the total resistance. Okay, we know that the V sub S, okay, let's say the V sub S, let's say V sub S is equal to, let's say 5 volts, okay? That's the total supply voltage. We know the V sub S, but we don't know the total resistance. So first, we need to get the total resistance of this circuit. Okay, and the total resistance of this series circuit is simply the resistances of all the resistors combined. Okay, added. So we have 10 ohms for R1, we have 20 ohms for R2, we have 30 ohms for R3, and then we have 10 plus 20 is 30, 30 plus 30 is 60 ohms. So we have a total resistance of 60 ohms. Okay, that is one of our answer because that is one of the question, the resistance of the given circuit, total. So how do you find the total current? The total current we can now find by having V sub S is 5 volts. That's the supply voltage over 60 ohms. So 5 over 60, that is 0.083. Okay, 0.083 amperes. Or in engineering notation, in milliamperes, that is 83.3. Actually, this is 0.083, I just rounded off. Okay, and if you're going to have an engineering notation, that should be 0. Or 83.3. Milli means times 10 raised to negative 3. Okay, so don't be confused. So common current ratings are in this form: milliamperes, microamperes, nanoamperes, and even picoamperes. Okay, so we did find the total current and the total resistance. So it's time to find the total power. And we know that we can find power by three formulas. In this case, okay, we have the IT. Okay, we can use the formula IV. So of course, we have to use the total current multiplied by the supply voltage because this is the total power. So the total current is uh, 83.3 times 10 raised to negative 3. Okay, I've written it in a scientific notation to denote that that milli is equal to this 10 raised to negative 3. 83.3 milliamperes is still equal to 83.3 times 10 raised to negative 3 amperes. Or they are all equal. This one, and this one. Okay? So, and that is multiplied to V sub S. Total voltage, we have 5 volts. Okay, if we are going to add that, so that is 0.0 or 83.3 times 10 raised to negative 3 times multiplied by 5, that is 0.4165 watts. Or in engineering notation, just press the eng in your calculator, button, so that it would be converted into engineering notation. So 416.5 milliwatts or times 10 raised to negative 3 watts. Okay, so far we have found the total current, the total power, and the total resistance in each circuit, in this given series circuit. How about calculate the voltage drop in each resistor? Calculate the current through each resistor. Now, if I'm going to ask you, what is the current through each resistor? Let's try to find first the current through each resistor. From what I have discussed a while ago, the current in a total circuit, in a series circuit, is simply equal to the current through each resistor in a series circuit is simply equal to the total current. Okay, so we have this relationship a while ago. So we have three resistors. So we have IR1, IR2 is equals to IR3. And they are all equal. Why? Because they are connected again in series. So the current through each resistors R1, R2, R3 is simply equal to, yes, 0.0833 amperes or 83.3 milliamperes or 83.3 times 10 raised to negative 3 amperes. Whatever value is that, okay, they are still the same. Okay, whatever notation you use. Okay? So, but it is more appropriate to use 83.3 milliamperes because that is in engineering notation. Okay, again, they are still equal, but this is in engineering notation. Okay, we already solved the current through each resistor. Okay, they are all equal to the total current because they are connected in series. But how about the voltage drop in each resistor? So what will we do? Okay, we can calculate the voltage drop at resistor 1. Okay, remember this Ohm's law. We can find the voltage drop in resistor 1 by applying Ohm's law. So we have V is equals to IR. Okay? And VR1 is equal to the current through resistor 1, of course, the current in through resistor 1 multiplied by the resistance of value of R1. So what will happen? So IR1 is 83.3 milliampere. Okay, if you're going to input this into your calculator, that's 83.3 times 10 raised to negative 3. Not just simply 83.3 because you would get a wrong answer. Okay, so it should have, this is milli, stands for milliampere. Okay, multiplied by the value of the resistor 1, which is 10 ohms. Okay, if we are going to multiply that 83.3 times 10 raised to negative 3 times 10, we have 0. Or okay, or 800. So if we're going to multiply it, okay, by in decimal, so we'll be having 83.3. Oops, again, multiplied by 10, that should be 0.833 volts. Okay? So that's the voltage via Ohm's law, by Ohm's law, voltage drop across R sub 1. How about voltage drop across R sub 2? Remember that they don't have the same voltage drop, not unless they have equal resistances. And since they don't have equal resistances, then they have different voltage drops. So for VR2, same formula, but this would be the current at current 2, resistor 2, current through resistor 2, and then we have the value of the resistance of 2. So we have still 83.3 milliamps multiplied by R2 is 20 ohms. So we expect the voltage drop here in uh, resistor 2 is much greater than compared to resistor 1. And by our calculation, that's 1.666 volts. Okay? So, lastly, we can get the voltage drop at resistor 3, wherein same formula, we have IR3 multiplied by R sub 3, and that is 83.3 milliamperes multiplied by 30 ohms. And of course, since it has a high resistance, its voltage drop is greater than R1 and R2. So we have 83.3 milliamperes multiplied by 30. So that would be 2.499 volts, or approximately equal to uh, 2.5. So that's it. So how do we check if we have gotten the correct voltage drop? So to check, if we add this all of this voltage drop, it should be equal to 5 or approximately equal to 5 because we have rounded off some values. So if we're going to do that to check, the total voltage is in a circuit is simply equal to the supply voltage, and that is equal to the voltage drop of R1 across R1, voltage drop across R2, voltage drop across R sub 3. So this is V sub S, and we have this V sub S is equals to 5. So this must be 5 volts is equal now to, okay, if we add, let me just erase this. So if we add this 3, it should be equal or approximately equal to 5. So if we add that, so we have first 0.833 volts plus we have 1.666 volts. Oops, sorry. So we have volts plus 2.499 volts, if I'm not mistaken. Am I correct? Yes. So if we add that, let's add 0.833 plus 1.666 plus 2.499, that is 4.998, which is approximately equal to our supply voltage, which is 5. So we have actually calculated the voltage drop, okay, correct. We have some discrepancy in the decimal here, but because we rounded off some values. Okay? So starting from the current a while ago. Okay? But that's one way to check it. Okay, so how about we are done with the calculate each voltage drop in each resistor. We are done with that. So how about the power dissipated by each resistor? Remember that the power dissipated by each resistor, okay, are not the same because they don't have the same resistances. So, as you all know, we recall the three formulas for power, and we have these formulas. So, to get the power at resistor 1, the power dissipated by resistor 1, we can either use of these three, because we already know the voltage drop at R1, we know the value of R1, so we can solve for the power using this formula. We also know the current in R1, and we know the value of R1, so we can use this formula. Or we know the current through R1, and we know the voltage drop through R1, so we can use also this formula. So what will we use? We use IV, okay, for simplification. So we have IR1, and of course the voltage drop at resistor 1. So, again, the current in IR1 is equal to the total current, which is 83.3. So, we have 83.3 milliamperes multiplied by the voltage drop at 1. So, we have 0.833 volts. So, upon multiplying, we have 83.3 times 10 raised to negative 3, 0.833. Okay, that is by notation, okay, by notation we have 0.0693889, and if we're going to have it in engineering notation, we have 69, let's say 69 point with 2 decimal 39 milliwatts. Just press the eng function in your calculator and it would show you automatically the value. Now, times 10 raised to negative 3 means milli. For PR2, we have IR2, the current through resistor 2, and the voltage drop through resistor 2. And of course, the current is still the same because they are again connected in series. And we have the voltage R sub 2 that is 1.666 volts. So we have a value of 83.3 times 10 raised to negative 3, 1.666. So we have 0.1387778 watts. Okay, this is in terms of watts, is equal to engineering notation, that is 138.78 milliwatts. Okay, so milliwatts means 10 raised to negative 3. Okay, that's a very small amount of power. Finally, for PR3, still the same formula. We have IR3, the current through R sub 3, and we have voltage drop across resistor 3. So we have 83.3 milliamperes multiplied by 2.499 because that's the voltage drop at the uh, third resistor. So we get a 0.208167 watts, and by engineering notation that is 208.17 milliwatts. So that's the power dissipated by each resistors. Okay, if we add this three powers, PR1, PR2, we will get 416.5 milliwatts, approximately equal to that because we have rounded off some values. So if we try that, okay, we add these three. So it's the same, 416.34, where in here we have 0.5. It's a little discrepancy, okay? But still it's near to 416.5. Okay? So that's how you try to solve some basic series circuits. Okay, the current, the total resistance, and the voltage drop across its resistors. Okay, so we haven't studied yet any techniques here, only the Ohm's law and some basic concept in series circuit. Okay, so if you found this video helpful, if you are new to my channel, please don't forget to subscribe and leave a comment down below. And please don't forget to watch also my other videos in circuits. So I'll be having a series of videos in electrical circuits for engineering. So thank you so much for listening, and I hope you learned something for today's lecture. Thank you so much. God bless you. This is again Engineer App.